Okay, so we're going to do this one. This was a request from a couple people that I do more of these. These were called exponential equations with the same base. Well, the problem is they're not the same base, and I tried to throw as many tricks at you as I could. So do you guys want to work it out, or do you want to watch me?
Watch you.
Watch me. Okay. So dig deep inside. What is the lowest base that each of these could be reduced to?
3.
What are they? How much?
6.
6.
I'm sorry.
So this is come on, stupid. This is 6 squared to the 3x plus 1 times 6 to the x minus 1 equals 1 over 6 squared to the 4x minus 2. That would be my first step. Okay. Looking inside of all of the base numbers and then saying what's the lowest base they all have in common? 6. Now, this particular one is a power raised to a power, so you can multiply them. So this is 6 to the 6x plus 2 times 6 to the x minus 1. Okay, this one over here has a 6 in the denominator, but we can't have it there, okay? Because all of these were implied 6 in the numerator. So you flip it by calling this 6 to the negative 2 to the 4x minus 2. Because all of these have to look like a 6, not a 1/6. Okay, so anything, remember, negative powers allow you to flip. Usually we go from negative into 1 over 6 to the positive. Usually we go from a negative power to a positive power. But there's nothing in the rules that say you can't go backwards if you needed to. These two things are identical, so you can flip them back and forth as long as you put the corresponding negative there. So this will become 6 to the negative 8x plus 4, because again, this is a power raised to a power. Over here, I made a comment. We were talking about a lot of things, so I understand confusion. But we want these to be a single base. We want to be able to condense them into a single base. So now the rule that we used, we said, for example, if you have x to the 3 times x to the 7, the rule was keep the base x, add the powers. That was the rule. So we're going to follow that rule. We're going to keep the base 6, add the powers 7x plus 1. All right, so where's my eraser? I want to stop there and open it up to any questions anybody has, anybody needs clarification on any single step. You're okay with finding base 6. You're okay with turning 1 over 6 into 6 to the negative 2 power. Negative powers flip.
That the 1 over 6 squared, that
Yeah.
only works if it's a 1 on top, right?
No, it this problem only works if there's a 1 on top. But the flipping of a negative power works in any situation. But this particular problem would only work if there's a 1 on top. For example, if you had 7 over 6 squared, and for some reason, you could call that 7 times 6 to the negative 2. You could flip the x up or the 6 up if you wanted to.
Okay.
Okay,
Catch it on.
but this problem requires that when we flip it up, there's nothing else up there other than just a 6, because we want to have all 6s.
Okay, I get it now. I see.
Okay. All right.
Thank you.
So, yeah, I'm sorry.
No, I just said thank you.
Okay. So what about power raised to a power? You guys okay with that? We did it twice. Power raised to a power, we multiplied them together, keep the base, raise or multiply the powers. This one, power raised to a power, we did that. But then we had to do one extra step where we had 2 6s, base 6s, and we had to condense them into a single base 6. So we had 2, we have to condense them into single, and the rule was keep the base, add the powers. So we get there. So are we okay to that? All right. Then we used some logic at this point. We said, oh, if the base numbers are the same, then the powers had to have been the same. So at that point, we could drop the base numbers and say they were unimportant to us. So 7x plus 1 equals negative 8x plus 4, and go ahead and solve. I think that's 15x equals 3. So x is 3 over 15. Where's my glare? Oh, I missed it. So solution set 1/5. And I'm done. Okay. Yes or no? I mean, several people asked for another one of these problems. Are we okay?
Okay.
Yes,
Okay.
that was good.
That's true for everybody who is asking for extra help?
Yeah,
an
I feel better
extra-
about it.
Okay.
Yeah.
Enough to kind of give it at least a try and yell at me over the weekend, or Ann or somebody. Okay. All right. So
Could
that's
you
that
just
one.
explain to me, Professor,
Go ahead.
how you got the 15x equals 3? Sorry.
Oh, added 8x to both sides. Okay, let me show
Okay,
you.
got it.
You okay with that or not? So this is just back to linear solving. So I add 8x, add 8x. Where's my glare? I'm okay. Okay, so that's what gave me 15x plus 1 equals 4. Then I took 1 away, so I have 15x equals 3, and then I divided and reduced.
Got it. Thank you.
Yeah. Anybody else? Okay. Next problem. I want to erase. I need to erase this. Actually, I need to erase a lot. How many people are here? Most of us. I'll wait a few more minutes. Let me put the problem over here to have you guys work on. I'll leave this up here for a little bit, but I have to erase it eventually. What I want you to do is I want you to graph, okay, y equals 3 to the x plus 1. I want you to label the asymptote, okay, and label the y-intercept, and state the domain and the range. So I'm going to pause. I have to erase this problem over here in a minute. So again, the way I've been suggesting you do this is building a table of values. So when x is 0, this is worth 2. 3 to the 0 is 1, plus 1 is 2. When x is 1, this is 4. Okay, when x is 2, this is 10, and that's good enough. And remember, I've said repeatedly, you don't have to do all the numbers I'm doing. You only have to do enough to give you the general shape of the graph. If you only need a couple of positives and a couple of negatives, great. If you need a bunch of positives and a bunch of negatives, that's great also. Just enough to give you individually the idea of the shape. So then we go to negatives. When x is -1, we have 1/3 plus 1, which is 1 1/3. When x is -2, okay, 3 to the -2 is 1/9. Plus 1 is 1 1/9. And for me, that's good enough. You might want to go to one more if x is -3. Okay, that turns out to be 1/27 plus 1, which is 1 1/27. And if you want to use decimals instead of fractions, go right ahead. It doesn't matter to me at all. Okay, so we're going to build a graph now. 0, 2. 1, 4, 2, 4. Okay. I don't have room for 2 10s, so I don't care about it. 2, 10. -1, 1 1/3. So that's about there. If x is -1, I go up 1 and a little bit. If x is -2, I go up 1 and even a little bit less. And that gives me the shape of the graph. That's good enough. So I know generally that this graph is going to look like that. Now, I haven't done any of the special stuff yet, but that's the basic shape of an exponential curve, an exponential graph. So is that okay with everybody or not? Any questions?
Okay.
No. Okay. So now, asymptote. The asymptote is the invisible line that the graph does not cross. Okay. What is it? Where is it?
What?
1. Because what I'm hoping you can see is that as x gets more and more negative infinity, okay, these numbers are staying 1, but they're always 1 and a little bit more. So we just say 1 is the asymptote. So we sketch it in here as a dotted line, and we label it as y equals 1. That's the asymptote. Label the asymptote means label its equation. Okay. Now remember, the equation itself is trying to give you a hint. That 1 is probably the asymptote in this type of problem. Okay, so there's the asymptote. Label the y-intercept. Okay, a y-intercept occurs when x is 0. So when x was 0, 2, so we'd already put it up there. That was the y-intercept. Okay, so I've labeled my asymptote. I've labeled my y-intercept. Are we okay with that one, guys?
Yes.
Okay, next, domain and range. The domain refers to all possible x's. Okay, well, on our table, we see that x can be positive and x can be negative. But question, does x stop at +2? Or does it go on? Does x go beyond +2? Well, way beyond.
It keeps
Does x
going.
stop at -3? No.
No.
The graph shows it goes on forever. So what's our domain?
Negative infinity to positive infinity.
Yep. or you can go fancy R depending on what mom will allow. They mean the same thing. Or if you really want to get confusing, you can say the set of all real numbers. All of those symbols, all of those words mean exactly the same thing. That's your choice, what you want to use, what makes sense to you, what helps you. Okay, range. Okay, if domain refers to all possible x values for this problem, range refers to all possible y values. Okay. I find it easier to look at the graph to study the range than it is to look at the table. The graph shows me better what the range is. Anybody want to take a shot?
1 comma infinity.
1 comma infinity with parentheses or brackets?
Yes, parentheses.
Yes. And I would say that's 100% correct. The y values, which are the up and down y values, they start at 1, but don't touch 1. That's why the parenthesis. And then they just keep going up. That's why the infinity. Is that okay with everybody?
Yes.
Okay. Last one on this problem. I'll pause it while you guys think about it. We talked about the inverse of a function. And one of the main steps in calculating the inverse of a function was to swap the x's and the y's. Okay, the inverse of a function, in working with the rule, we swap the x's and the y's. So if you go look at the notes, one of the things I did is I gave you a sketch and asked you to sketch its inverse. I gave you a chunk, don't write this down. I gave you something that looks like that or whatever. And we sketched the inverse. So what I want you to do on this problem is sketch the inverse. And see if you can. Think about it. I'm going to do it on the same grid. You may want to do it on a separate piece of paper in case you screw up. But we'll pause while you think about it. Okay, so here we go. This might get really messy. To sketch the inverse, we're going to swap the x's and the y's. So instead of 0, 2, we're going to plot 2, 0. 1, 2, 0. Instead of 1, 4, we're going to plot 4, 1. Instead of 2, 10, we're going to plot 10, 2, which is sort of like here. So already I can begin to see my curve a little bit. Now it gets trickier. Instead of -1, 1 and 1/3, I'm going to go backwards, 1 and 1/3, -1. So this was 1. So 1 and 1/3, -1 is kind of like right there. I'm guessing it's close enough. Okay. 1 and 1/9, comma, -2. 1 and 1/9, -2. So I can see the graph looking like that. Now there's one more thing I want to add to this. Okay. Actually, before I talk about the one more thing, are you guys okay with the concept of how do you make the sketch of an inverse? You just simply switch the ordered pairs and graph the switched order pairs, and that's the inverse curve.
Professor, so the formula just changes up top, pretty much? the y equals 3x, it's x.
Give me, yes, it would be that, but we'll cover that in much more detail next week.
Okay.
Your concept is correct, but you couldn't go further than that. Yes, you swap the x's and the y's. We're going to do some simpler examples of exactly that in just a minute. But this is actually a very complex problem in order to find its formula for the inverse. We're just sketching the inverse. We're not finding the actual formula or rule. Okay, I kind of cut you off. Are you okay?
Yes,
By
I
the-
got it.
Okay, by the way, are you feeling okay?
Yep, hanging in
Oh,
here.
good.
Thank you.
Yeah. All right. Now, here's one last thing. The original graph had an asymptote of y equals 1. Okay. If you swap all x's with y's, the new graph will also have an asymptote. But what will its equation be?
X equals 1.
Bingo. X equals 1, and that is a vertical line like that. So to sketch the inverse, all x's get swapped with all y's. And then you just graph from that point onward. So there, by the way, is a question, maybe not on the chapter 10 quiz, maybe, I don't know, I haven't looked at it. I guarantee that's a question on the chapter 10 exam. I guarantee that. I'll give you some formula, ask you to graph it, label the asymptote, the y-intercept, state the domain and range, and I'll also say sketch its inverse. I guarantee that's a question on the chapter 10 exam right there. So put a star on your notes on that one. Okay, I want to go forward. A couple more review questions. And this will answer a little bit of what Richard was getting to a second ago. Can I erase the board?
I'm okay.
Okay, I don't hear anybody else yelling. We okay?
I'm good.
All right. Now, a couple things. Quizzes tonight. We already know that. If you didn't see this over here in the module chapter 10, I put a worksheet there called log laws. Log laws. We're going to start them tonight. Okay. But you're going to kind of want this worksheet in front of you as you do a lot of your homework next week. And I'm going to be referring to this worksheet next week. So sometime between now and next week, try to download that worksheet. Okay. And it would help if you can actually do it on paper, because it'd be really nice to have it in front of you while you're doing your homework, while you're listening to my lecture notes and stuff like that. Also, one other thing. Hello, those of you who went to sleep, wake up. This is important. A couple persons have told me that they've been doing the chapter 7.6 homework. Okay. And yet when they went back and looked at it, mom zeroed them out. Mom said, yeah, I don't care what you did. If this is you, go back and look at your homework tonight or whenever. And mom gave you a 0 for 7.6. Okay. Send me a quick email saying something like, mom cheated me or something like that. And I'll give you full credit. If you tell me you did the work, then I'll just give you full credit. But send me an email. Okay, here we go. I have a question. Why is my heater turning on? God. Okay.
It's been cold here.
Well, not here, not where I am. I mean, it's cool, but it's not turn on the heater. Oh, well. All right. Here we go. Couple more problems and we'll get into some new stuff. Suppose f of x is 3x minus 7, and g of x is 2x plus 9. Okay, so with those, I want you to find the following. I want you to find f composed with g of 2. B, I want you to find g composed with f. C, I want you to find g composed with g. And D, I want you to find g inverse of x. And when I say that, I mean find the rule or the formula, not the sketch, but the rule. Okay. So I'm going to find out why my heater's doing what it's doing, come back in about 3 or 4 minutes. Okay. Little quickie review. Let's go to B for just a second. When I write G composed with F, it is also the same as G composed with F of X. The X is assumed there. So when we do this, this stands for G of F of X. We say it from left to right, but as we actually write it, we put the X into the F function and we put the F function into the G function. So this notation, G circle F, okay, means G of F of X. Well, I guess since I'm doing this one, I should finish this one off before I come back here. So this says take the F function and take all of this and plug it into G. Well, what's the G function do? It says go 2 times whatever you give me. So I'm going to go 2 times F of X, and then I'm going to add 9. So that's 2 times 3x minus 7, add 9. 6x minus 14, where's my glare? Okay, plus 9. So this is 6x, what's that, minus 5, I think is the answer. And that's just simply the answer. Remember, what you're doing is you're taking 2 rules, 2 separate rules, G circle F, and you're condensing them into one big fat rule. So instead of doing 2 rules separately, you say, oh, I can just do this and that'll be the same change. Remember, a function changes a number. So instead of doing 2 changes, I can do one big change and get the same answer. That's what that's saying.
I have a question.
Yeah.
So you went from the first problem saying that the first G times F.
No, it's not
yeah.
times, it's G circle. Say G circle. G circle F.
Okay,
It's not
so
timesing.
so you said it's the same thing as the bottom, right? The
I
second
just,
there?
I'm
I'm
sorry.
trying to
Yeah,
understand.
these two are the
trying to
same.
understand how-
The X is implied. When we write it here, this without an X, the X is implied. So this and this are the same thing.
Okay.
And actually this, where my hand is,
Mhm.
and this are all the same thing. They're just
Okay.
different ways of writing the same thing. Is that okay?
Yes, thank you.
Okay. For letter B, is that okay with everybody? Okay. Now, coming over here to A, F of G of 2. Well, this is F of G of 2. Okay. Now, this is a little bit different because we could actually calculate G of 2. We were doing that way back at the start of the semester. See, we can't calculate F of X. Okay. There's no answer for that. It's just that. Okay. But we can calculate g of 2. That literally says plug 2 into the g function. So g of 2 is 2 times 2 plus 9. So this becomes f of 13. 4 plus 9 is 13. So the subtlety here is you plug x into f and then you go, well, crap, I can't do anything. So you just keep working it out. But here we plug 2 into g and go, oh, I can work that out. I can plug a number into there. But now this becomes f of 13. So what does f say? I go 3 times 13. 3 times 13 minus 7. That's 39 minus 7. That's 32. And that's just your answer. Questions on part A. F composed with G, or F circle G of 2.
Got 30. I messed up, I think.
So for the answer, you write f of g
Of
2
2.
equals 32.
Or just circle the 32, yeah. 32 is good. It's more a way of getting you guys to do it a little arithmetic. If you just circle, like on this one, 6x minus 5, fine, I'm happy. If you just circled 32, cool, I'm happy. Okay. But technically you are correct. I should be writing F circle G of 2 is worth 32. That's kind of like the concluding statement to this work. But if you circle 32, I'm happy. Vince, you ever figure out what you did?
Yeah, I put instead of minus 7, I made a second put the 9 on the outside again.
Oh, okay. All right, so we okay with part A and part B with everybody? Okay, now this becomes, remember the X is implied. So part C is G of X. So we're sticking the G into the G. Well, what's G say? The G says, whatever you give me, I'm going to times it by 2 and add 9. So I'm going to take 2 times the G that I'm giving it, times by 2, plus, whoops, plus the 9. Okay, so what is that? That's 2x plus 9 plus the 9. So that's 4x plus 18 plus the 9. That's 4x plus 27. And that's the answer. That's G of, or G circle G, or G composed with G, or whatever. How are we doing? I'd like to erase this first problem, F circle G of 2. I don't have enough room to do it over here. So can I erase problem A? Is anybody still writing this down?
I'm good.
Okay. All right, here we go. Now, Richard was asking this problem, alluding to it, but he was asking for the inverse in a much more difficult problem, which I said the difficult ones we'll deal with next week. But if you have G of X equals 2x plus 9, now I'm doing this problem. I'm finding G inverse. The rules were first write it as y equals 2x plus 9. Then swap the x's and the y's in the rule, just like you swapped them in the graph. Okay, just like you flip-flopped x's and y's in the graph, you flip-flop x's and y's in the rule. But for the rule, we have to then solve for the y, get y alone. So we take away 9 from both sides. And then we divide everybody by 2. And then I said you must at the end replace the y with, okay, the inverse. And you're telling everybody that this problem, this formula, I should say, and this formula are not some random ones that Foster made up in a drug-induced haze. They are actually related to each other, okay, because they're the inverses of each other. And the point of an inverse is to cancel out. If G changes a number according to this rule, then G inverse takes the changed number and changes it back to the original number. So G inverse undoes the change. And with that, I pretty much reviewed everything we've been doing this week, with the exception of logarithms, which we'll get to in just a second. So, questions about finding the inverse of a function, the steps, you should have it in your notes. Okay. Finding the composition of a function, that's what that's called, putting a function inside of another function, or any of the other problems.
How did you check it last time? I remember you did the inverse to, I don't remember exactly, but you like checked the number. Make
Oh,
sure
I
it was-
just made up a random number. I just said, okay, for example, suppose I wanted you to find G of -2. Okay, so you plug it in here, you get 2 times -2 plus 9. That's -4 plus 9, whatever, that's 5. So what this says is G took -2 and turned it into 5. Okay, so what's supposed to happen if we take G inverse of 5? If life is good and I haven't screwed up, it should change it back to a -2. Okay, G changes -2 into a 5, according to the rule that we had here. So G inverse should take 5 and change it into a -2. That's what's supposed to happen. Well, let's see what happens. Okay, G inverse of 5, we take 5 minus 9 divided by 2, because that's what it says. Whatever you're going to give me, I'm going to go 5 minus 9 divided by 2. Well, 5 minus 9 is -4. Where's my glare? Divided by 2. I can't see it. Crap. 5 minus 9 is -4 divided by 2. Yep, it turned it back into that. So that's what I was showing you a couple of days ago. And I just randomly picked up a number. I just picked a number, plugged it in, and then tested it.
Gotcha. Thank you.
Yep. Anybody else? Okay. What time? Okay, plenty of time. Plenty of time. This was all review. So in your notes, you might want to indicate that that was mostly review of 10.1 and 10.2. 10.1 and 10.2. Everything we did up there. I think the first problem was maybe 10.3, that same base problem. But I don't know if it was or not. I'm confused. All right. But we are definitely right now going to go and do some more work on chapter 10.3. Okay. And in 10.3, I introduced the concept of logarithms. I started with it and how you have to write log base B is low of 7 equals 25 or something like that. Okay. Let's put the base down here of 5 or something crazy. Okay. So we talked about having to write that thing. It's called the base. Okay. And it's written lower. And also to say it in English, you say log of 7, comma, base 5. You must mention the base. Then you can either say is or you can say equals 25. That's up to you. Or you could say log, comma, base 5 of 7 is or equals 25. But whatever, you need to mention the base. Okay. That's because in a minute, it'll make a lot more sense. But one of the things we talked about last night was something called the common, I should write it neater, called the common log. And that when you write like the log of 7 and you don't write the base, it's automatically assumed. It will always be assumed to be base 10. That's called the common log. It's base 10 log. So if you don't say the word base 5 or base 3 or whatever, okay, if you don't say that, everybody will assume you meant base 10. And they will all get different answers than you implied or that I implied. So that's called the common log. It's assumed to be a base 10 if I don't write it. Always, even on your calculator, even in the textbook. We also introduced something called the natural log. Natural log. And it was the ln of 7. And there's some discussion. How do you pronounce ln? Is it literally ln? Okay. Or so do you say ln, not no? That's too much Spanish. Ln. Okay. Do you say lawn, LAWN, which some people do? Or do you say the natural log? And pretty much the whole math science world is split. There's no consensus which one of these is the better way of saying that.
Where did
Okay.
lawn come from?
I don't know. Rodney King, can't we all just get a lawn? Get it? Never mind. That's it. That's a famous quote of his. And yet, how far have we gotten from Rodney King? Not very. I don't know. People didn't want to say LN and they didn't want to say natural, so they said lawn. I don't know. I don't have a good answer for you. Okay. All right. Bet you didn't think I'd get political with Rodney King when we're talking about logarithms, did you?
Not at all.
Yeah, there's a good one. I don't even know if anybody even remembers that, or his statements, rather. Okay, so this is kind of briefly, and we learn to use our logarithm calculator buttons a little bit. We'll get more practice. But now I want to tell you what a logarithm actually is. I just said, okay, here's a logarithm, and we're going to talk about it, and this is how you say it, and all that other crap. But what is a logarithm? So here we go. A logarithm, a log, is a weird exponent. Okay? A logarithm is a weird exponent. When you write the log base 3 of x equals 2, there's a this is called a logarithmic equation. It's an equation because it's got an equal sign. And it's logarithmic because it's got the word log in it. Okay, so this is a logarithmic equation. This is equivalent to, and I'm going to write a double-headed arrow, and I'll explain why in a minute. This is equivalent to the exponential equation of 3 to the 2 equals x. This logarithmic equation, log base 3 of x equals 2, is the same thing as this exponential equation, 3 to the 2 power equals x. They're identical to each other. Okay? So the double arrowhead implies that if you have this exponential equation, you can change it into a logarithmic equation as long as you put everybody in the right place. And they're the same. Or this logarithmic equation is the same as this exponential. One of the jobs we're going to learn tonight, and you as a student must learn to do in your sleep, okay, or in a drunken stupor, whatever, you must learn how to switch from logarithmic to exponential and exponential into logarithmic just instantaneously and in your sleep. Okay, now I've seen a couple ways of doing this. Okay, this is what I remember. I call this the bar-bra rule. B-A-R-B-R-A. Okay. No other instructor in the world uses this, as far as I know. And if they do, they're not giving me credit. Okay. If you have the log base B of A equals R, if you have a logarithmic equation, log base B of A equals R, it is equivalent to B to the R equals A. Okay. So if you start at the bar, log of a bar, you end up with the bra. B to the R equals A. Okay. Mostly because I don't want to get fired anymore.
Makes sense.
I had a long story that once upon a time was cute and funny and relevant, and now I can't tell it because I'll get sued. Okay, but the gist of it is, if you start with log of a bar, log base B of A equals R, you start with bar, you can end up with bra, B to the R equals A. Okay, this gives us a formula, a way to transpose an equation. So suppose I gave you log base 2 of x equals 5. Okay, can you convert that into an exponential? Log base 2 of x equals 5. That's logarithmic. You write the exponential. And if you did it right, it should be 2 to the 5 equals x. Yes or no?
Yes.
Okay.
Yes.
A lot of people learn this circle thing. They say 2 to the 5 equals x. I've seen a lot of people do that. Okay. I don't care what method you use to go from logarithmic to exponential or exponential back to logarithmic, as long as you get it right. It doesn't matter bar, bra, circle methods, some other method, you just got to get it right. So how about this one? What if I gave you log base x of 64 equals, wait a minute, 81 equals 4. Log base x of 81 equals 4. Can you convert it to exponential? And it should be x to the 4 equals 81. Yes or no? Okay. So we kind of okay with that? We're going to do a few more, but I want you to notice something. This first, let's go back and look at this one. Look where I'm pointing. Log base 2 of x equals 5. Okay. Currently, there's no way to do that problem. But if you change its form here, if you change its form, suddenly you got x alone, and you can work out 2 to the 5. Turns out to be 32. So the advantage of this bra bar stuff, or logarithmic converting from one to the other, is that sometimes you will not be able to solve a problem as it's written. Okay. But if you convert it to a different format, you can solve it. It's easier to solve. Same thing down here. This problem, this original problem, as it's written, why isn't somebody telling me I'm in the glare? Crap. Okay. So this is x to the 4 equals 81. I'll do it that way. Okay. Yeah. So this original problem, okay, can't be solved. Not as it looks, but by converting it to an exponential problem and messing around with it a little bit. For example, I'll show you, if you have x to the 4th equals 81, and you take the 4th root of both sides, you get x equals, all right, the 4th root of 3 to the 4th power is 3. You can get an answer. Now, maybe you guys wouldn't have seen it right away, but we got a couple weeks of practice on this stuff. But my point is, by being able to change it from one form into a different equivalent form, you can change a problem that's unsolvable into a problem that is solvable. And that's most of the game with logarithms. So what if I gave you, well, we need to do some work here. Okay, what if I gave you 3 to the x equals 15.9. 3 to the x power equals 15.9. Okay, I can guess x is somewhere between 3 and 4, because think of your powers, 3 to the, no, between 2 and 3. 3 to the 2nd is 9, 3 to the 3 is 27. So this is somewhere in between. So the answer is somewhere between 2 and 3. I can guess, but I don't want to guess. I want to be much more accurate. So here's my first comment. convert this into a logarithmic equation. Use the Barbara rule or whatever to convert this to logarithmic. So you should get log base 3 of 15.9 equals x. Is that okay with everybody? Everybody. Utilizing this pattern. It's not a rule or even a formula. It's a pattern that you're following. Okay, but wait a minute. Last night, we talked about using our calculators. Okay, we talked about using our calculators. Some of you have a base 3 button on your calculator. Others have to divide this into log of 15.9 over log of 3. So go ahead and try that on your calculator. .51801. You guys get that or not?
Yes, I got
Yeah.
this something.
Okay, let me see if I can do it using the magic button. Log base 3 of 15.9. And I get the same answer.
I tried
Okay.
to plug that back into the 3x equals 15.9, but it didn't come out the way I wanted it to.
Did you plug in 5.180 or did you plug in the whole decimal?
I just did 3 answer and then did that.
And it didn't come up?
It's 159 over 10.
Well, what is 159 over 10? 159 over 10 is 15.9.
Yeah, you're right. I'm sorry.
Okay. Yeah. I see it's okay. Okay. By rounding this, I was assuming that you had rounded this. And by putting a rounded answer back here to check your work, you probably wouldn't get 15.9. You'd get something really close, but not exactly. But since you used a whole lot of the decimal, it should have come out exact, and it actually did. All right. Let's try
Professor,
another one.
quick question.
Oh, okay.
On the right there, we have log of 15.9 divided by log over 3. Does it matter how you write that? If it's log over 3 over log divided by log?
Yeah, the big number is on top, the base is on bottom.
Okay, that's
always.
why it's a base. Got it. Okay.
The base is on bottom. Base 3 is goes to the bottom. And notice what we've actually done is we've converted this into base 10s. Because remember, I wasn't writing anything. I just said log of 3. Well, it implies to be log base 10 of 3. So for your question, base 3, the base always goes in the bottom. However,
Thank you.
do you have that magic? Which calculator do you use? The 36X?
Yes.
Then you have that magic button. If you press the LN log button a couple of times, okay, you're going to get log blank blank. And you should be able to put a 3 here and a 15.9 here and get the same answer without having to worry about the division.
True. Got it. Thank
Okay.
you.
Yeah. So I mean, what I'm trying to, I don't want people to run out and buy a new calculator. Okay, because this little step here isn't worth the trouble of going out and buying a new calculator. It just isn't. If you have this feature on your calculator, for God's sakes, use it. All right, let's try another one. Okay. Okay. New example. 5 to the x equals 2.5. See if you can solve that.
I'm sorry, that's 25 or 2.5?
2.5.
Oh, okay.
So if we write it as a logarithm, we would have log base 5 of 2.5 equals x. And then however you choose to do it, base 5 of 2.5. I get 0.56932, whatever, equals x. Again, the directions on directions on my quiz, whatever, it'll tell you what to round to. But if you're getting that answer, you're doing it correctly.
What does base actually do to the equation?
Well, what does base do? What does base do to an exponent? 3 to the 2, or let's go, what if we did 3 to the 5, 2 to the 5, 17 to the 5? The base means something raised to that power, okay? This is a different thing. So this base here says, if I take 5 and I raise it to some power, okay, how do I get 0.25 or 2.5? I'm not answering the question well.
I'll just stick to the calculator. School. I just was curious, like understanding.
Okay. I'm not sure I have a clear answer for you yet until we get into some other problems and some graphs, but keep asking that. But I want to show you something very important in this conversion that has bearing on what you asked. I'm not deflecting, I'm doing this. Remember I said, I made a big deal about how to write this as log base b of a. You had to say base b. Well, remember in an exponent, that's called the base. Remember, that's the exponent, and that's the answer, whatever that is. Okay, so the base of the logarithm, log base b, is always the base of the exponential. The base is the base. Okay, so whatever you see here, 5, that means it's going to be the base, the base of the logarithm is the same thing as the base of the exponent. So it's saying 5 raised to this power is worth x. Or excuse me, 5 raised to the x power is worth 2.5. 5 raised to the x power is worth 2.5. They're saying the same thing in different format, except in this logarithmic format, your calculator can do your work. In exponential format, your calculator can't, but it's still an exponent. Well, that's all I can tell you. The base is an exponent. And
Gotcha, I get it now.
you get different answers, okay, with different bases. That's all you get. Okay. And I did want to make this point very clear that the base of the logarithm is the same as the base of the exponent. So when you're converting from one to another, the base is the base, always. The base of the exponent becomes the base of the logarithm. That might help you. Now, okay, I'm keeping an eye on time. I've given you just enough to get started in section 10.3 on mom. She just has you switching back and forth between a logarithmic equation and an exponential, or between an exponential and a logarithmic equation. Okay, she just has you doing a bunch of problems where you're switching back and forth from one format to the other. Occasionally, she will ask you then to go ahead and solve. So stop for a moment and look. Okay, here's an exponential. What if mom says, write this in logarithmic form? Then you write this and you quit. Okay, if mom says, write this problem in logarithmic form and then evaluate if possible, then you write the logarithmic form and then you evaluate. Okay, so you got to read the directions. This is exponential form. This is writing it in logarithmic form. And if mom says that's all she wants, that's all she wants. If she says, oh yeah, by the way, evaluate it, then you go one step further. Use your calculator and plug it all in and that kind of crap. So, but most of section 10.3 in mom is switching from one form to the other and backwards and forwards, just to give you guys practice. Now, I want to start, okay, by introducing some basic log laws, basic laws of logarithms. And the first and the most basic, okay, the number one thing you have to know is the Bra-Bar rule. Log base b of a equals r is equivalent to b to the r equals a. That's the number one rule. You got to know it in your sleep, and you got to know how to apply it. Now, next rule. Log base b of b. Okay, so let's come over here to this for a second. What if I wrote log base 3 of 3 equals something? I don't know what. Convert it. This would be 3 to the x equals 3. 3 to the x power equals 3. Well, wait, what's the only thing x can be? 3 to the x power equals 3. What's the only thing at what?
1.
1. Huh. Okay. What if I wrote log base 7 of 7? And I said, okay, it equals y. Now convert it. 7 to the y equals 7. What's the only thing y can be to make that problem true?
1, I guess.
1. Y has to be 1. So come back over here. Log base b of b is always worth 1. You can instantly simplify your problem. Bingo, just like that. Log base b of b. So if you ever see log base 15 of 15, you go, screw that. The answer's 1. Okay. Log base 2.5 of 2.5, forget it. The answer's 1. Okay. That's what that rule says. The log base b of b. So if those two numbers are the same, the answer will always simplify to 1. Now, if you can't remember that, your calculator will show you that. But the more you know, the faster you can work through a problem. All right, rule number 2, or number 3 rather. Okay. Log base b of 1. Log base b of 1. Well, let's see. What would that look like over here? Let's go. Log base 3 of 1 equals something. I don't know what. Log base 3 of 1 got to equal something. So again, apply the bra bar rule, and you have 3 to the x equals 1. Well, wait. What's the only thing x can be to make that a true statement?
0.
0, right. X has to be 0. All right, let's try it again. Maybe that was a fluke. Log base 7 of 1 equals x. So you apply the bra-bar rule. 7 to the x equals 1. Again, x has to be worth 0. So we get this cool rule. Log base b of 1 is always 0. Always. So if you see a problem that says log base, 9.6 of 1, you go, well, heck with that. The answer is 0. Is that all right with everybody? We got one more rule to get, and then I want to show you one thing, and then we're done. So these are our 3. We're going to get one more very basic rule. Okay, and this rule is a little bit harder to explain. So for tonight, for lack of time, I'm going to use the tried and true, shut up and memorize it. And I'll be able to explain it better on Tuesday. So the 4th basic rule, number 4, suppose you had the logarithm base b of, I don't know, x to a power. Example, suppose I had log base 3 of 7 to the 4th power. So regardless of the base, you got a base b, you got some number there, I don't know what it is, but you've got it raised to a power. This is known as the power rule. You're allowed to pull this power out in front as 4 times the log base b of our base 3 of 7. The power rule for logarithms says you're allowed to pull the power out front as a multiplier. Okay, now that's pretty cool because if you're doing this on your calculator, okay, you'd have to go 7 to the 4th power, figure that one out, and then do log base b of that big ugly answer. This is saying, no, you can do log base 3 of 7 on your calculator, get it, and then multiply it by 4. So the rule I'm trying to show you here is the power comes down, p times the basic stuff, log base b of whatever x was. So what if I wrote log base 2 of 9 raised to the 5th power? how can you convert that to something a little bit simpler using the power rule?
5 times log of,
Yep. It's 5 times, you bring the 5 out in front, 5 times the log base 2 of 9. And that will help make some problems simpler. So that sheet I asked you to download, it's in module 10. Okay, it says log laws. These are on them, but you kind of also need to know these to do some of the problems in chapter 10.3. Some of the mom problems, you could really benefit from knowing these. Okay, it makes your work so much simpler if you knew these instead of having to work through a bunch of crud. Okay, I want to do one last thing, and then we'll get ready for the quiz. Okay, I want to graph y equals log base 2 of x. I want to make a graph of that. Now, you could be like Mitch and go to Desmos and graph it, and it'll do it for you. Okay, Desmos will graph it, and you can look at it and check your work. But there's 2 ways of doing this. Okay, one way is to build an XY table and use your calculator and just get a whole bunch of silly decimals here. Okay. The other way is to use the bar rule to convert this. So take a second and see if you can convert that to an exponential. Notice right now it's called a logarithmic equation because it's got a log in it. Convert it according to the bar rule to an exponential. Remember, the base of the logarithm and the base of the exponential have to be the same. So this is going to be 2 to the y equals x. Is that okay with everybody? That's using the bar rule to convert my logarithmic equation into my exponential equation. Are we okay or not okay? All right. Well, then the next question is, well, so what? Well, watch. It's much easier to build a table of values from this problem than it is from this problem. But in this case, we're going to start with y. What if y were 0? 2 to the 0 is 1. X is 1. What if y is 1? 2 to the 1 is 2. What if y is 2? 2 to the 2 is 4. Okay, you can go on, but notice what I'm doing. I've converted the equation from a logarithmic into exponential, and I'm picking y values, plugging in y to get to x. Well, let's try some other ones. What if y is -1? 2 to the -1 is a half. What if y is -2? 2 to the -2 is a fourth, not negative. And that's good enough for me now because now I can graph it. Okay. 1, 0, right about there. 2, 1, right about there. 4, 2, right about there. Okay, look at the shape of this already. Looks like that. 1/2 comma -1. Right about there. 1/4 comma -2. Right about there. Okay, so look at the shape of the graph. Okay. Based upon our discussion of exponential curves, take a wild and crazy guess. What about this graph right here? As it comes down, will it ever touch the y-axis?
No.
Probably not. Okay. So in this case, the y-axis becomes its asymptote. Now we'll talk more about that next week. But this is an easy way to graph by hand a logarithmic. You cheat. You change it to an exponential. You write a set of ordered pairs derived from the exponential, and then you plot it and you use some of your intuition, and you're going to get that graph. That's a logarithmic curve. That's the graph of a logarithm. And if you want to see what it really looks like accurately, go to Desmos. Okay. With that, I think the thing should open in 5 minutes. I know some of you indicated that you had questions, so I'm going to pause right now, or I'm going to stop my recording.